Welcome to the deep dive.
Okay, let's unpack this. This past week, the cosmos gave us something really special, didn't it?
It certainly did.
That stunning total lunar eclipse, the one everyone calls a blood moon.
Yeah.
It was just, wow, a global thing. Seeing the moon turn that deep, sort of mesmerizing red.
Yeah, like a cosmic ember, as you say.
For those of us tracking these celestial events, it was, well, pretty extraordinary. A great reminder of the dance happening above us. So let's dive into what made this one stand out.
Exactly. And our mission today, really, is to go beyond just the beautiful pictures. We want to unpack the precise science that paints the moon red.
Right.
And also maybe cut through some of those myths that always seem to pop up around eclipses.
Oh, definitely.
And kind of put it all in perspective why these alignments are not just cool to look at, but genuinely valuable for science and, well, just a unique shared human thing.
And what a shared experience it was. I mean,
Yeah.
if you saw it, that transformation, that striking red color, just unforgettable. It really felt like that, didn't it? Like the whole world paused for a moment to look up.
Yeah.
And the scale was immense. This total lunar eclipse, estimates suggest it was visible to somewhere between 5.8 and maybe over 7 billion people globally.
7 billion. Wow.
Think about that reach.
Yeah.
Asia, Europe, Africa, Australia, the Western Pacific, huge stretches of the Indian and Eastern Atlantic Oceans.
So pretty much everywhere except...
Except North America, unfortunately.
Yeah.
They largely missed out this time. But for, the vast majority of the planet, it was prime viewing.
That visibility alone makes it unforgettable. And the event itself, the timing, it was quite substantial.
It really was. Totality, that's when the moon is fully inside. Earth's darkest shadow lasted a remarkable 82 minutes.
82 minutes. That's quite long for totality.
It is, and the whole eclipse from the very start to the very end spanned about 3 hours and 29 minutes.
Wow.
So, just for context, in parts of Asia, say India, totality was late night, like 11:01 p.m. to 12:23 a.m. local time.
Right.
But then, flip to the other side of the world, like Eastern time in the U.S., and it was happening mid-afternoon, roughly 1:30 p.m. to 2:52 p.m. ET, even if they couldn't see it.
And what's really interesting is how people reacted. It wasn't just scientists watching, was it? It felt, cultural, communal.
Absolutely. You saw organizers setting up public viewings, live streams like that one at MHA Tower in Langkawi. Lots of people sharing the moment.
Yeah.
And for many communities, it had spiritual significance too. Like Muslim communities performed the Salat al-Kusuf prayer.
Ah, the eclipse prayer.
That's right, a special prayer for eclipses. And importantly, for everyone keen to watch, astronomers were quick to confirm, totally safe for the naked eye.
Which is great, unlike a solar eclipse where you need all the gear.
Exactly. No special filters needed for this one. Just look up.
Which meant, more people could just be part of it. And the photos. My goodness, they were flooding in from everywhere, weren't they? Ancient Athens, bustling Tokyo.
Sydney, Berlin. Just incredible shots. It really felt like a shared global moment captured visually.
It really did. But, okay, beneath that beauty, there's some fascinating science. So when the moon goes into Earth's shadow, the umbra, you called it.
That's right, the umbra.
What's actually happening to the light to make it turn red?
Yeah, that's the million-dollar question, isn't it?
Yeah.
It's all about alignment. Earth gets perfectly positioned, sun, Earth, moon, all in line.
Okay.
So Earth's shadow falls right onto the moon, and specifically the moon travels into the darkest, the very central part of that shadow, the umbra.
And I know, and our listeners who follow this know, it involves something called Rayleigh scattering. Maybe we can dig into how our atmosphere does that. How does it turn the light red?
Yes, let's. So imagine sunlight heading toward the moon. Before it gets there, it has to pass through Earth's atmosphere, right?
Right, through our air.
And as it does, the tiny molecules in our air scatter the light. But they're much better at scattering the shorter wavelengths, the blues and violets.
Okay, so that's why our sky looks blue during the day, that scattered blue light.
Precisely. That blue light gets scattered all over the place. But the longer wavelengths...
The reds and oranges?
Exactly. They're more, let's say, resilient. They punch through the atmosphere more directly.
Ah.
They do get bent or refracted by the atmosphere, kind of like going through a lens. And this reddish light gets directed towards the moon, which is sitting in the shadow.
So the moon reflects that bent, reddish light back to us.
That's it. The moon basically gets illuminated by all the sunrises and sunsets happening around the edge of the Earth at that exact moment, all projected onto its surface.
That sunrise and sunset analogy really clicks. Does that mean the conditions in our atmosphere at the time actually change the color we see?
Absolutely it does. The exact shade Whether it's a deep blood red, a more coppery orange, or even a sort of rusty brown, it really depends on what's floating around in the atmosphere globally at that time. Things like dust, clouds, moisture, even volcanic ash can make a big difference. They affect how much light gets scattered and how much gets bent.
So each eclipse is a bit unique in its color palette.
Definitely. Makes each one subtly different to watch.
It's amazing how our own planet paints the moon. But this blood moon, this total eclipse, isn't the only kind, right? There are other types.
That's a very good point. Total eclipses where the moon goes fully into the umbra are the most dramatic.
Uh-huh.
But you also get partial lunar eclipses. That's where only, well, part of the moon dips into the umbra. You see a dark bite taken out of it.
Okay.
And then there are penumbral eclipses. The moon only passes through Earth's fainter outer shadow, the penumbra.
Those are harder to notice.
Very much so. Often it's just a subtle shading, easily missed, unless you're really looking for it. And the reason we don't get a lunar eclipse every single full moon,
Yeah, I always wondered about that.
it's because the moon's orbit around Earth is tilted. It's tilted by about 5 degrees compared to Earth's orbit around the sun.
Ah, so they don't line up perfectly every month.
Exactly. Most months, the moon passes just above or just below Earth's shadow during the full moon phase.
Yeah.
You need that precise alignment for an eclipse.
That tilt makes these events much rarer. It's incredible how much we understand now, isn't it? Especially when you think back to how people used to view these things.
Oh, absolutely. Historically, eclipses were, well, often terrifying, steeped in folklore, superstition.
Seen as bad omens.
Very often, yes. Across so many different cultures, they were interpreted as signs of danger, divine anger, major upheaval. The variety of beliefs is just fascinating.
Can you share some examples? What did ancient cultures think was happening?
Well, take India, for instance. There's a tradition where families stay inside, they avoid cooking, even avoid handling sharp tools during an eclipse.
Really?
Yeah. Some Aboriginal Australian traditions also saw them as ominous. The ancient Egyptians had myths about a great sow swallowing the moon.
A sow.
Okay.
While in China, the classic story is of a celestial dragon trying to bite or devour the moon. People would bang pots and drums to scare it away.
Wow. Bang drums to save the moon. And even today, you still hear some strange myths kicking around, don't you?
You absolutely do. It's surprising how persistent they are, despite, science.
Like the idea that pregnant women shouldn't go outside during an eclipse. Something about birthmarks.
Yes, that one comes up a lot. Or the idea that food prepared or left out during an eclipse becomes unsafe or poisoned.
Right, I've heard that too.
And science, of course, tells us that's just not true. Physical traits like birthmarks are down to genetics and development in the womb.
Nothing to do with moonlight or lack thereof.
Precisely. And eclipses have absolutely zero effect on food safety. They don't impact our health, our mental state, or trigger natural disasters like earthquakes, another myth you sometimes hear.
So the takeaway is beautiful, natural, totally safe to watch.
Completely safe. Enjoy the view. Pregnant women, people having picnics, you're all good. Science says relax.
That's good to hear. And speaking of history, isn't there that famous story about Christopher Columbus using an eclipse prediction? Ah, yes, at the 1504 eclipse in Jamaica. It's a classic tale, maybe slightly embellished over time, but rooted in fact.
What happened?
Well, Columbus and his crew were stranded. Relations with the local Arawak people were deteriorating, and they weren't getting enough food.
Okay.
Columbus had astronomical tables, an almanac, that predicted a total lunar eclipse was coming. So the story goes, he warned the Arawak chiefs that his god was angry and would take away the moon as a sign.
Uh-oh.
And right on schedule, the eclipse began, the moon turned red, and apparently the terrified Arawak quickly agreed to provide the needed supplies.
Wow. Talk about using science to your advantage.
A pretty dramatic example of applied astronomy, for sure.
Beyond these sort of historical power plays, how have eclipses actually helped science itself, helped us understand things?
Oh, immensely. Even back in ancient Greece, observing lunar eclipses provided some of the first real evidence that the Earth was round.
How's it?
By watching Earth's shadow creep across the moon, philosophers like Aristotle noticed it always had a curved edge, regardless of Earth's orientation. Only a sphere consistently casts a circular shadow.
That's clever. Simple observation.
It was. And fast forward to today, we're still using them. NASA's Lunar Reconnaissance Orbiter, LRO.
Yeah, the LRO mission.
It actually uses the rapid temperature drop on the lunar surface during an eclipse to study the terrain.
How does that work?
Its diviner instrument measures how quickly different areas cool down when sunlight is blocked. Big rocks cool slower than fine dust, so it helps map out rock distribution and understand the surface properties, like density.
So even now, these ancient alignments are giving us fresh data about the moon.
Exactly. Still scientifically valuable.
Okay, so maybe listening to this has got you inspired. You want to capture the next one yourself. For anyone thinking about astrophotography, what's the basic gear?
It's a great hobby to get into. You don't need a space telescope, but some basics really help. A DSLR or mirrorless camera is usually best, gives you manual control.
Right, and lenses.
Lenses are key. For wide shots, showing the landscape with the eclipsed moon, something like a 14 to 20 millimeter lens works well. But for those dramatic close-ups,
You need a telephoto.
definitely a
Yeah.
good telephoto or zoom lens. And absolutely crucial, a sturdy tripod. Essential to avoid blurry shots, especially during longer exposures.
Makes sense. Anything else?
A remote shutter release is really helpful. Stops you shaking the camera when you press the button. And if you're doing longer exposures, maybe for wider star fields, including the eclipse, a star tracker can be a game changer. It moves the camera to counteract Earth's rotation.
Okay, got the gear. What about settings? Where do you even start?
Right. First, shoot in RAW format. Always. It captures much more data than JPEG, giving you way more flexibility when you edit later.
Good tip. RAW mode.
Use manual mode on your camera. You need full control.
Yeah.
Keep your ISO low start around 100 or 200 to minimize noise.
Okay, aperture.
Aperture, maybe around f5.6 to f8. That often gives a good balance of sharpness and light gathering for lenses. And shutter speed. That's the tricky one.
Why?
It really depends on the eclipse phase. During totality, when the moon is dimmest, you might need speeds from, say, 12/50th of a second up to maybe even 1 second or slightly more. You have to experiment.
It's that balancing act of the exposure triangle.
Exactly. ISO, aperture, shutter speed. You'll be adjusting them constantly as the eclipse progresses. Practice helps.
And composition. Any quick tips on framing the shot?
For tight close-ups, usually centering the moon works well. But if you're including landscape elements, think about the rule of thirds. Placing the moon off-center can make it more dynamic.
Right.
And definitely plan ahead. Use apps like PhotoPills or Sky Safari to see exactly where the moon will be in the sky from your location. And of course, check the weather forecast. Clouds are the enemy.
Excellent advice. Fingers crossed for clear skies next time. So speaking of next time, if we miss this blood moon, what's coming up? When's our next chance?
Good news is, the cosmos keeps delivering. While this September 2025 total lunar was a big one, there's more on the celestial calendar. There's actually a partial solar eclipse quite soon, September 21st, 2025. Visible mainly down South Australia, Antarctica, parts of the Pacific and Atlantic.
Okay, solar. Need filters for that one. What about lunar?
The next total lunar eclipse, the next blood moon, is set for March 3rd, 2026.
March 2026. Where will that be visible?
That one should be viewable from Asia, Australia, the Pacific Islands, and importantly for listeners who missed out this time, the Americas should get a good view too.
Good news for North America.
Yes. And there's also a partial lunar eclipse later in 2026, August 27th, 28th, visible from the Americas, Europe, Africa, and Western Asia. So plenty more opportunities lining up.
That's great to know. It really is. Well, incredible, isn't it? The whole spectacle, these alignments, knowing we can predict them, understand them, even photograph them, it's quite profound. So what does this all mean for you listening right now?
I think it's a chance to reflect on just how special these moments are and maybe how transient. Here's something to think about. The moon isn't fixed in its orbit. It's actually drifting away from Earth.
Drifting away. Slowly, I assume.
Very slowly, yes. About 1.5 inches or maybe 3.8 centimeters per year. Sounds tiny, but over cosmic timescales.
It adds up.
It really does.
Yeah.
Scientists estimate that in about 600 million years, the moon will have drifted far enough away that it will appear too small in our sky to completely cover the sun.
Wait, so no more total solar eclipses?
That's the prediction.
Yeah.
Total solar eclipses, that perfect fit we see now, might just be a temporary phenomenon in Earth's long history.
Wow. Okay, that puts things in perspective. We're living in this privileged window of cosmic time.
We really are witnessing these perfect cosmic coincidences.
So the message is appreciate them. Appreciate these fleeting, breathtaking alignments. Stay curious. Keep looking up. You never know what amazing sight the universe has in store next.